Let's say we have a linear transformation of this nature, and we want to find the image of V, which is the 2, -5 vector. And then maybe the preimage of W equals 1, -6. Now we can think of T as acting on a vector space V, mapping that vector space to vector space W. So V is an element here, and W is an element of here, over here. So V takes V onto the image of V. Kind of cramped. And W has a preimage in V. Okay, well, image of V. Well, T acting on V is T acting on 2, -5. And by the rule, that's got to equal, well, -3 times the first component of the vector, so that's -3 times 2. And then 2 times the first component, which would be 2 times 2, minus 4 times the second component, which is -5. And that then equals -6. That's 4. That's 20. So -6, 24. What's the preimage of W equals 1, -6? Well, let's let U be the preimage. Then the transformation acting on U would be 1, -6. Well, let's assume that U equals U1, U2. So, -3 U1, 2 U1 minus 4 U2. I'm not leaving myself enough room, so I'll obliterate that. So, T of U equaling U1, U2, just like we have here, is -3 U1, 2 U1 minus 4 U2, and that should equal 1, -6. Well, this leads directly to a system of equations. We have then -3 U1 equals 1, and 2 U1 minus 4 U2 equals -6. Now this is an easy system to solve. U1 is then going to be just -1/3. Plug that in here, we get -2/3. Add that over here, we get -5 1/3. We divide that by -4, and 5 1/3 is 16/3. You divide by 4, you get 4/3. You check that out. So we have this. Or if we prefer, this becomes -3, 0, 2, -4, multiplied by U1, U2 equals 1, -6. It's an invertible matrix. You can invert it, or you could do a row reduction, either directly from the system of equations or from this matrix equation, and you could find U1, U2. In the process, it should be easy to see that T applied to any vector is equal to negative 3, 0, 2, negative 4 times the components of that vector. So that this matrix defines this transformation, and vice versa, the transformation defines this matrix.